Picture this. You're locked in an intense gaming session. Victory is within reach. Suddenly, the game freezes. Your character becomes unresponsive. You're left staring at a frozen screen, your heart pounding with a mixture of frustration and despair. We've all been there. These agonizing moments of lag can turn even the most patient gamer into a raging keyboard warrior. But have you ever stopped to wonder what causes this digital hiccup? The culprit is often hidden deep within the heart of your computer, a tiny chip known as the Central Processing Unit, or CPU. The CPU is essentially the brain of your computer, responsible for executing every instruction and running every program. However, even the most powerful CPU can't do everything at once. This is where CPU scheduling comes in. CPU scheduling is like an invisible traffic cop directing the flow of tasks within your computer. It determines which programs get to use the CPU and for how long. Just like a traffic cop managing a busy intersection, the CPU scheduler ensures that everything runs smoothly, preventing digital gridlock. But what happens when the traffic cop isn't doing its job effectively? Chaos ensues. Programs fight for CPU time, leading to those dreaded lags, freezes, and slowdowns. Understanding CPU scheduling is key to unlocking the full potential of your computer and ensuring a smooth, frustration-free computing experience. Imagine the CPU as a nightclub with a single, highly sought-after dance floor. Outside, a long queue of eager partygoers representing computer programs clamors to get in and show off their moves or execute their instructions. The CPU scheduler acts as the discerning bouncer, deciding who gets access to the dance floor and for how long. The bouncer can't let everyone in at once. That would lead to chaos and a very unproductive dance floor. Instead, the bouncer employs a set of rules, known as scheduling algorithms, to determine the order and duration of each partygoer's time on the dance floor. Some bouncers might prioritize those who have been waiting the longest, known as first come, first served. Others might favor those with shorter routines, ensuring everyone gets a chance to dance, known as shortest job first. There are even bouncers who randomly select partygoers, adding an element of fairness known as round robin. Each scheduling algorithm has its own advantages and disadvantages. The choice of algorithm depends on the specific goals of the nightclub, such as maximizing the number of dancers, minimizing wait times, or ensuring fairness. Similarly, operating systems employ different CPU scheduling algorithms based on the desired system behavior, such as responsiveness, throughput, or resource utilization. Let's delve deeper into the world of CPU scheduling algorithms, exploring their unique characteristics and real-world implications. Imagine you're at the grocery store, and the CPU scheduler is the cashier managing the checkout lines. First come, first served, or FCFS, is the simplest algorithm, much like a single, long checkout line. Processes are executed in the order they arrive, regardless of their size or complexity. While fair, this method can lead to long wait times if a single large process gets stuck at the front of the line, blocking everyone else. Shortest job first, or SJF, prioritizes processes with the shortest estimated execution time, similar to an express checkout lane for customers with only a few items. SJF minimizes average waiting time but requires knowledge of process execution times, which isn't always readily available. Round robin, or RRR, gives each process a fixed time slice on the CPU, ensuring no single process monopolizes the processor for too long. Imagine the cashier rotating between customers, scanning a few items from each before moving on to the next. RR excels in time-sharing environments, providing a fair and responsive experience for multiple users. Priority scheduling assigns priorities to processes, allowing higher priority processes to take precedence over lower priority ones. Think of this as a VIP lane at the grocery store, where customers with special privileges get expedited service. Priority scheduling is crucial for real-time systems, ensuring time-critical tasks receive immediate attention. These are just a few of the many CPU scheduling algorithms employed by operating systems. The choice of algorithm depends on the specific requirements of the system and the workload it handles. Section 4. Real-life impacts. When CPU scheduling goes wrong. The consequences of inefficient CPU scheduling can be far-reaching, impacting everything from gaming performance to battery life. Remember that frustrating game lag we talked about earlier? That's often a direct result of poor CPU scheduling. When the CPU scheduler fails to allocate sufficient time to the game, it struggles to keep up with the demands of rendering graphics, processing input, and updating the game world. This results in dropped frames, stuttering gameplay, and a frustratingly unresponsive experience. Similarly, slow video exports can be agonizing, especially for content creators working on tight deadlines. When the CPU scheduler prioritizes other tasks over the video encoding process, it slows down the export, adding precious minutes or even hours to the rendering time. But the impact of CPU scheduling extends beyond performance. Battery life, a constant concern for mobile device users, is also heavily influenced by how efficiently the CPU is managed. When the CPU is constantly switching between tasks or running unnecessary processes in the background, it consumes more power, draining the battery faster. Section 5. The future is now AI and the evolution of CPU scheduling. The future of CPU scheduling is poised for exciting advancements, driven by the transformative power of artificial intelligence and machine learning. Researchers are exploring innovative ways to leverage AI to create smarter, more adaptive scheduling algorithms. Imagine a CPU scheduler that can predict the future behavior of programs, anticipating their resource needs and proactively allocating CPU time to prevent bottlenecks before they occur. This predictive capability could significantly enhance system performance and responsiveness. Machine learning algorithms can analyze past usage patterns, identify recurring workloads, and optimize scheduling decisions based on historical data. This data-driven approach could lead to more efficient resource utilization, extending battery life, and reducing energy consumption. The integration of AI and machine learning into CPU scheduling holds immense potential for creating a more intelligent and efficient computing experience, paving the way for a future where lag becomes a distant memory. Section 6. Beyond the surface. Appreciating the unseen work. CPU scheduling might seem like a hidden technical detail, but its impact on our daily computing experience is profound. It's the unsung hero working tirelessly behind the scenes to ensure our computers run smoothly and efficiently. The next time you're engrossed in a game, editing a video, or simply browsing the web, take a moment to appreciate the intricate dance of CPU scheduling happening beneath the surface. It's a testament to the ingenuity of computer science and the countless hours of research and development that have gone into creating this essential component of modern operating systems. Section 7. Have you experienced the lag? We've all felt the frustration of a lagging computer, the agonizing wait for a program to respond, or the disappointment of a dropped video call. These experiences, while frustrating, highlight the crucial role CPU scheduling plays in our digital lives. As we venture further into an era of increasingly demanding applications, from immersive virtual reality experiences to complex data analysis, the importance of efficient CPU scheduling will only continue to grow. Understanding the fundamentals of this critical process empowers us to make informed decisions about the technology we use and appreciate the unseen forces that shape our digital interactions.